distributed databases. In particular, is going to focus today on distributed transaction processing. Just a couple of announcements. I did post for those of you doing final projects. I posted a sign-up sheet, so these are for meetings next week to come talk to me about where you guys are in your project. I listed some suggestions for what you should come to the meeting prepared with. And are there any questions about anything? You guys good? Yeah?
You can't make any this time.
Just send me an email. We'll find some other time. All right, take it away, Eric.
Anyone have any questions from last week at all? We're back in the world of distributed parallel databases today. So like Sam said, we're going to be talking about distributed transactions. I write TXM for transactions short a lot. Sam writes, X action, so hopefully you can do that. We're going to talk about a protocol called two-phase commit, which I will abbreviate as 2PC, but I will write it up as two-phase commit. Yes, not to be confused with two-phase locking, 2PL. We've talked about 2PL a lot. Two-phase commit is different. It's important to keep those separate in your mind. We'll also talk a little bit about distributed locking. And we'll cover a little bit of replication. More or less the agenda. So two-phase commit. When we talked last time, we talked about these kind of shared nothing databases. This is the world we wanted to move to. And there was the question of what do we have to change for concurrency control to make shared nothing databases work? I wanted to partition my database, separate it so different physical nodes have different data. The data is actually fragmented or partitioned. How do I have to modify our concurrency control to make it work? And there's a solution. Obviously, that solution we're going to talk about is two-phase commit. So we can think about, well, why do we need this? At a conceptual level, if we had some transaction, and the transaction started, and we did an insert of record A, an insert of record B, an insert of record C, and then we wanted to commit. Our transactional ACID properties, we want all of our ACID, right? Atomic, consistent, isolated, and durable. Well, we had this partition database role. These inserts might actually go to physically different servers. Right? The insert of A might go to server 1 for site 1, B might go to site 2, C might go to site 3. So can anyone see what the issue might be here if we're in a distributed environment and we wanted to maintain transactional correctness? What's the scenario that can go wrong? I know it feels like Monday. I'm slow. Myself especially. Right. The key property of a transaction is that we want it to be atomic, all or nothing. So we send out these commits to these 3 sites. But what happens if somewhere along the line this site goes away? If it crashes, and the other 2 sites take that and they say, okay, I wrote that insert and it's committed now. But site 1 doesn't have record A. So is this a ACID transaction if that happens? No. Right? We have a problem there. We had something that happened, a transaction happened, that shouldn't have happened. S1 crashed. So S2 and S3 should not have applied that update. Another notion that we might want to have that we haven't really talked about, which we can apply in this context, is a distributed transaction. Here we might want to begin operation, maybe read a record. Then we might want a sub-transaction inside this. I want to write some other record. We want to write another record and commit this. And if this commits, we might want to do something else and then commit this global transaction. Here in this case, we might want the sub-transaction to execute on a different site. In this case, we want this to execute, and only if that executes correctly, we want that nested, the outer transaction, to actually commit. So we need an architecture in order to support these things. So we need to think about how can we change these protocols to do this. So we have the user, the application. What we need is we need some kind of leader. We need somebody to direct everything. So this leader is going to talk to what we're going to call as the coordinator. The coordinator is going to be responsible for ensuring that the transaction goes through, maintaining the properties that we want to have. So what the coordinator is going to do is it's going to talk to all of the sites that it needs to in order to make the commit happen. We're going to call these other sites the subordinates. Let's abbreviate subordinate. So in that example, we had A, B, and C going to S1, S2, and S3. We could think that S1 is subordinate 1, S2 is subordinate 2, S3 is subordinate 3. So queries are going to arrive at the coordinator. It's going to be issued to the coordinator. The coordinator will distribute that to the subordinates. When a commit happens, that commits to the coordinator. The coordinator is going to make sure that everything happens in a consistent manner. So let's talk about how this is going to work. So if you think about that operation, the coordinator here is going to talk with these subordinates here. In the first case, what we want to do is we want to do that insert. Right? We have that first record, insert A here. Insert A. Site 1 will let it know that's okay. If that goes forth, then we can insert B in site 2, get the confirmation, and then you do the insert C with the other one here. This is more or less what we wanted to do before. But now at this point in time, we can have a failure from that. A failure can go wrong at this point. Have these inserts happen, something can still go wrong. So what do we want to do in this case? Well, what we're going to do now is we're going to issue prepare statements. To the sites. And the prepare is the coordinator telling the subordinates to get ready. We're going to do a commit. Are you ready to do this commit? And the subordinates are going to go back and say, yes, I'm ready to do this commit, or no, I'm not ready to do this commit. And once they've actually said that they're going to do the commit, they're actually committed to doing it. So this is where the two-phase part of this two-phase commit comes into it. There's 2 rounds of communication. We have the prepare phase to say, is everyone ready to do it? And then we'll follow it up with the commit phase, where the coordinator is actually going to tell the subordinates that they're going to commit. This seems complicated, right? It seems like a lot of excessive communication that we necessarily don't have. But there's a lot of things that can go wrong. From the time that the insert happens, to the time that we tell them to prepare, the site could have failed. There could have been an issue with that site serializing the transaction against other transaction execution happening at that site, or this coordinator doing global serialization. You might have a laptop down. So we need to have this prepare phase in order that all the sites can get in line, and we can have a durable process that ensures serializability. And this is all going to be done through this prepare. Okay. So the coordinator is going to prepare the subordinates on the operations that have already been applied when a commit happens. The commit comes in. This is now we need to prepare and ensure that happens. We're going to go through the protocol in a little bit of detail because this kind of conceptually makes sense that we're going to have these 2 rounds. You have your operations applied, and then when it comes to commit time, we're going to do our prepare, check in with everybody, make sure everybody's good to go, and we're going to go back and forth and send out all the messages. How many here has actually taken distributed systems? All right, a good amount, but not everyone. So one thing that's important to think about when we're doing this protocol is you have to think about messages as being asynchronous. I'm going to send a message to the coordinate, to the coordinator, to the subordinate, and there's not a guarantee that that message necessarily got there or how long it's going to take. So you have to frame your mind in this world that things aren't necessarily real time. That there's delay between messages, and messages can be dropped, machines can fail, and they come back online. So you have to frame your mind in this context of how we're communicating. You don't want to think about it like everything's on one machine, messages are instantaneous. I know when a failure happens immediately, because a failure might take a while to actually be detected. And this is this nature of asynchronous messaging. You can think of it more like you're text messaging with people. If I send a text to somebody, there's not a guarantee that they get it right away. I don't know when they see it. It might be dropped. It might show up 30 minutes later because T-Mobile's network sucks. So think about messaging in more that way, not necessarily that they're on the phone with each other. So we're just going to talk about one subordinate right now who can kind of live in coordination with the coordinator. But just you can assume that this is going out to all the subordinates, one at a time, or in parallel, or so forth. So the commit message comes into the coordinator. Right? Whatever operations we've done before, these inserts, whatever operations they've been, it's now time that the transaction wants to commit it. So here's what's going to happen. The coordinator is going to go into a mode of preparing. And we'll send the message to all the subordinates. So prepare. The subordinate, when it receives this prepare message, it's going to write a log entry here. And I'm going to write FW, and I'll explain it in a second here. And it has to write whether it's going to commit or abort this operation. The transaction manager can abort a transaction for a multitude of reasons, so it has to make that decision locally if it can do it. But this is a force rate. And the protocol is really clear about this. When they go through and they illustrate, how do we have to do this? We want to write something to persistent storage. I want to make this protocol such that it can survive a failure, and a failure where the node goes down and comes back online. So it's not a failure where the node goes away and we never see it again, but it might crash and it might lose its volatile memory. When we went through all the transactional processing, this is kind of that world we were in. How do we log things to disk such that if I fail to recover, I'm able to rebuild my state with some component? So here when we talk about a forced write, we're talking about that this write has to have happened and everything pending before it relating to this transaction has to have gone to the disk. When you deal with systems, you can deal with asynchronous activity within the machine. When you write to a disk, your actual computer doesn't necessarily write that to the disk right at that time. It says, okay, I got it, I'll do that. But then if the machine shuts off at that moment, that write might not have actually went to the disk. The machine actually buffers that, and at a later point in time decides to write it down to the disk. And this is for performance reasons. Disks are slow. They were really slow back in the day. And this is why, and people don't worry about this as much today, but this is why they always say safely shut down your computer, because it's to make sure that any pending operations actually get applied. So when we say a forced write, it's a mechanism which a machine can say, I'm going to write this to the disk, and I'm not going to do anything until I know that write has actually been applied to the disk. So once this forced write has gone through, it's been written down to the disk, it can vote. And the vote is telling the coordinator that this is what I want to do in regards to this. And at this notion, we say it's in a prepared state. So once you've voted, you're prepared. If your friend sends you a message that says, hey, do you want to meet up at 7 o'clock on Friday? You get to have that deciding point. But in this world, once you tell them, yes or no, I'll be there, you're prepared and you're committed to it. That's what's happening here. Is it saying, I will participate in this transaction, I agree with it, or I won't? And all the sites have to send these votes back to the coordinator to say, here's what I think should happen. If the coordinator, it's all yeses, everyone checks in and says, we're good to go on this. What we know we can do is we can commit. So everyone says yes. The coordinator now knows all of my participants have agreed to go along with this, and they've all committed to doing this. The same analogy, if you're the one organizing all your friends and you text them all, you want to meet at 7 on Friday, and they all come back in and say, yes, we'll meet at Friday at 7, you know your plans are set for Friday at 7. So here what we have is we have a commit. Well, the individual subordinates don't know what's happening at this point. All they know is that they've individually said yes or no. So they're waiting to hear back from the coordinator. So the coordinator would need to notify everybody that it happened. But we have something here called the unilateral abort. One of the subordinates can cause an abort. All it takes is one. This isn't a majority. This isn't a dictatorship. The coordinator has no idea what's happening at the subordinate, so it has to ask them. So if one subordinate says no, it's no. And everything, it's basically a veto power. So in this case, if no one, or if at least one of them, would not give a yes, we have an else case. This is pretty simple in this case. We're just basically going to force write and abort. And after we force write and abort, simply have to abort. Tell everyone about it that we've aborted. So in this case, now these subordinates now can know that, you know what, that transaction that you told me to get ready for, that transaction I'm all prepared for, I don't need to do it anymore. So when we thought about transactional correctness too, going back, think about what's happening here. When we thought about how do we process correctness with transactions, when we talked at the beginning that we're talking about 2PC, not 2PL, then a lot of these cases are using 2PL to do correctness. So when we have a site that's been prepared, they've acquired locks on some set of data, and they're sitting on those locks. And they're not going to release those locks or do anything else until they know that they're done with that data set. So all these subordinates that have acquired locks are done, whatever kind of concurrency control mechanism, are locked on that. They're sitting and they're waiting. So they're anxiously waiting to hear, can I do this or should I abort this? You know, they want to move on with life. Once they've heard back, they want to go. If it's an abort or commit, you want to write to the log. You want to make sure that we've recorded what happens. And afterward, we can acknowledge. Say, hey, you know what, I heard about the commit or the abort, and then go back and tell the coordinator that everything is great. At this point in time, they can write the end. They can say, this is over. I've heard from everyone. We went through this two-phase commit. We went through these 2 rounds of commitment. Everyone checked in and said, that was great. We did it. I'm over now. I can write it to the disk, and I can move on with life, meaning I can forget everything about that transaction. Anything that I'm keeping in memory, anything that I prepared, or you know, what sites am I waiting on, which locks do I have held, can all go away at this point. They can write it.
Is that just a normal write then?
Yes, that's just a normal write.
Okay.
And we'll go through and talk about failures at the different points, and hopefully it'll illuminate why this can just be a regular write and not a force write. Does everyone get this part so far? This is a devil in the details type of thing, and it's a lot of little things that make it work, and sometimes it seems simple and sometimes it seems complicated. But we'll go through it and hopefully it'll make sense. So whenever we do a log write, we have to write some data out. So when we talk about these forced writes, we have to do something. So all records are basically going to write out the transaction ID and the coordinator ID. So anytime there's any record written, any of these writes, forced writes, anything related to this, they write down this information. If it's a prepare that's being written out, we need the locks that are held. What is this basically? If we ever prepare, what locks are being in the database do I know that are sitting there that are basically this prepare is blocking up on? So prepared, I'm waiting, I'm holding these locks to be prepared. Now for the coordinator, writes out a commit or an abort, he needs to know the list of subordinates involved. What subordinates are sitting as part of this process. So let's go through now and start talking about failures that happen at different points in this timeline, and hopefully that will illuminate why this is correct or what's going to happen in this case. Let's imagine the commit comes into the coordinator, and the coordinator fails. The coordinator, crashes and recovers and comes back up online. What do we think should happen here? It really is Monday-like, isn't it? Slow, quiet. The polar vortex is coming. Any guesses?
Nothing.
Yep, right. If we haven't committed it, we haven't gone through all the process of doing it, let's just abort it. This is what would happen on the regular system if we fail. If we're going through our regular concurrency control on a local machine, and we said commit, but we didn't go through the process of committing, we would abort that transaction and we restart it. Didn't go through the way of getting everything down to this, so I don't know what's going to happen. So in this case, we're just going to abort. So the coordinator, when it comes back online, can abort it. We don't know anything what happened about it. It's going to say, here I'm back online. We had some things that happened, but I don't know what else happened after that point, so I'm going to restart. Sorry. Commit or abort. Yeah, like do with the space that we have. So the subordinate in this case, it received some operations. It had some inserts, some reads, some writes that happened, and at this point in time, the coordinator died. So subordinate has to do something, because it had lots. It was waiting to hear, it's like your friends are sitting at home waiting to hear back from you about what are we doing Friday night. You haven't told them anything. But what are they going to do? Are they going to wait till Friday night at 7 o'clock before they make a decision? At some point in time, they're going to time out and say, you know what? Forget this. It's over. I'm not dealing with it anymore. I'm tired of the coordinator. And they have the ability to do that, right? This unilateral abort gives them the ability to do that, because you know why? When it came to this point in time, when they voted, they have the right to say no. So they can say no at this point in time. I haven't heard from you long enough, it's over, I'm going to quit. So we have a failure here. What is this going to look like? The subordinate fails at this point.
Sorry, so that's the subordinate has, it's been too long since it heard the pair from the court?
Yes. So it actually, we don't even know if it heard the pair or not. Right? This failure is ambiguous. If we recover, it might have gone out to some of them. It might not have gone out to any of them. It might have gone out to all of them at this point in time. But the failure happens right before the pair or in the middle of the pair at some point in time. But we just know that it has not reached this point yet. Yes?
When the coordinator fails and then comes back, does it not know the subordinates that it's talking to before it crashes?
No, it would not have a list of the subordinates at that point in time, I believe. Because it hasn't written them out to the disk yet. So it could probably reconstruct it if there was transactional information ahead of time and try to replay it and figure it out, but it's not necessarily stored in with the list of the coordinator at that point in time. But at this point in time, it necessarily doesn't even have to do anything. If it comes back online, you have to go through and let them know that it's over. The protocol can ensure that the subordinates will make progress without it. Because they have a timeout mechanism. At some point in time, the subordinates are going to give up, because that's what we talked about. The subordinates will give up and they'll move on. So say we have a failure here. Before we flush this right, we're going to give up again, right? Same thing. The subordinate fails. The pair went to it. It had it, but it hadn't written it to disk. What's the coordinator going to do in this case?
Resend up the pairs. Resend up the pairs.
It could resubmit the pairs. It could try to go through the process again. But odds are it's going to abort. It's going to take this case because it just go abort it and make to say it's over. I'm not going to do it again. It's going to abort the transaction. If the user wants to resubmit it, they can resubmit it. But in this case, we don't know what happened to the subordinate. It might be down, so it's just going to abort and say it's over. I haven't heard. That's partly done because we haven't gotten to that commit point. Any one of them can abort, so we might as well abort this time for correctness. When the subordinate comes back online, it's going to wake back up for fails and recovers, and it doesn't know what happened. So it's going to end up going through the same mechanism. It's going to roll back on that transaction. The transaction is over. Let's say we got here. One of the subordinates fails after it wrote its vote. Because it said locally, okay, I've heard about this prepare, and I've written to my disk whether I am going to abort or commit this.
And then it comes back. So if there's a first wrote commit, then it did agree, so it can respond to the vote.
So it can't, so it's already responded to the vote, right?
Well,
It may have.
When it comes up and vote.
Yes, it can vote. When you come back online at this point in time, all you've known, if you're the subordinate, you crash and you come back online, all you know is that I wrote this to this, I committed to voting. This crash could have happened before this, it could have happened after it. It doesn't write down that it did that. It doesn't say, hey, I voted, I saved that vote online. Because also, this message might not have ever even made it, even if it did. It could have failed some way. But all it knows is I've committed to doing this. If it said commit, it's committed, it's prepared. And at that point in time, that means I'm stuck with it Tell your friend you're showing up Friday at 7, you're showing up Friday at 7. That's what you said, you have to stick to your word here. So in this case, it might not have sent the vote. So it comes back online, but it knows it committed. So what should the subordinate do in this case? Can ask the coordinator. Can also just re-vote again. I can just say, I'm going to send that message again back to the coordinator, which is effectively the same thing. Just say, hey, here's the vote on that transaction that we talked about. I'm voting on it. It needs to do this.
So what if like it's like offline for a long time, does the coordinator lock on that?
So this is a good question. So the question was, what happens if it stays offline for a long time? What's going to happen in this case?
Abort.
At some point in time, if the vote never made it, the coordinator is going to treat it conceptually as this. Right? The coordinator doesn't know if it voted or not. So at some point in time, the coordinator is going to say, I haven't heard from this person. I'm going to abort it. If the coordinator did hear from it, then it's a different story. The coordinator now says they've committed to doing this. But now the coordinator is not necessarily as committed as the subordinate. The subordinate said yes and wrote it to disk. It's saying I'm stuck. I said I'll be there. But in theory, even if the protocol was correct, another subordinate could have said abort. In which case, the coordinator still has the ability to abort this transaction. So it can still say, this is over. I haven't heard from the subordinate long enough. I'm going to abort this and have it kind of just be over.
So what happens to the rights of that community?
So this writes up there. So what's going to have to happen in this point is it's going to have to reconcile. It's going to have to find out what happened. So in this case, it's kind of what David was just saying, is that when it sends the message or it asks about the transaction to say, well, what's happened to this transaction? The coordinator is going to get this message to say, well, hey, guess what? I voted on this transaction. I told you I can do it. Now what happened to it? So the coordinator in this case has to tell it basically that it's been aborted. So when the coordinator gets a message about a transaction, and it basically thinks that it's either over, or it still has it in a state that it knows it's over, it can say, you know what, forget about it, abort it, be done with it. So at that point in time, when it receives that abort message, it can abort it and go on with its business. Does that make sense to everybody? Okay. So let's say we get some kind of failure here. Anyone want to take a guess as to what's going to happen here?
You still just abort it.
So, yeah, going to have to abort it in this case. At this point in time, it fails, comes back online. It hasn't actually written out this commit. It's going to abort. It hasn't committed to that. It's going to let everybody know. Now, going back to the question that you just asked a minute ago, what if this stays down for a long time? What happens?
Subordinates have to assume the coordinator died.
They
And
have to
abort.
assume it, but what can they do about it? They've made a commitment that they're going to commit to this protocol. So they're kind of in this situation where they're stuck waiting on the coordinator. They've committed to this. Everyone else is potentially committed to it. So they're in this situation where this data has been locked. Now they have to wait to hear back from it. This is partly how this protocol can ensure correct. Because it doesn't necessarily know. If you think about it, one coordinator prepares, all the rest of them might have gotten the acknowledgement that this went through. Maybe they lost it. Their link went down. Something happened. The link is dead. But by the protocol, everyone else could have received it and committed that data, in which case it has to wait to commit that data and make sure that it's consistent with the other sites. Because if it did something inconsistent, our transactional guarantees are broken. This is when we have a coordinating process like this, we become dependent on it in order to say yes or no. It becomes a blocking protocol in this case. It's not guaranteed to be locked. When this does come up, you're going to have the case where basically the subordinates are going to check with the leader and say, what happened on this transaction? What happened? I need to know. So the coordinator's written the commit to disk. It's flushed it down to disk. So it fails, it recovers, it looks at its log, it's trying to pick back the pieces, what happened to its life, and it says, I received all of the votes and I wrote a commit. So what do we do in this case?
Tell the subordinates to commit.
We don't know if this went through. We can't be sure if it went through, so we need to let them know about it. So we'll tell the subordinates to commit again. They might not have gotten that message. We don't know. We're going to rebroadcast out these commits to all the subordinates and tell all the subordinates, hey, guess what? We've committed this transaction. You can go about your business. The subordinate receives a commit multiple times. All it has to do is act it. Right? If I get a commit from the leader, it necessarily doesn't know that the leader failed. It just knows that the leader told me to commit. I'm going to acknowledge it because that's what it wants to do. It wants to hear back from me. It's needy. But I'll commit it. But one thing that we know that could potentially happen here is that the subordinates are waiting. Right? They're dependent on the coordinator. So if the coordinator fails at this point, and it doesn't rebroadcast that commit message or that abort message, whatever the answer is, then it knows that it can have subordinates that are blocked on it and waiting for it. They're just sitting there, not making progress on the rest of their life because they need to hear about it. So this is what I'm saying. The subordinate has to hear back from the coordinator at this point in time in order to make progress. It's prepared and it's committed. However many are involved in the transaction. So, and what we're going to see, it's whatever sites went through. So we could have an unknown number of sites. We could have n sites. The transactional case that we've applied might only be to a subset of the subordinates.
Which one commits? Commit all commit?
Which ones will commit? So what's going to end up happening is the commits are really going to be the committed update. If you made any modification to data, let's say you received this message and you can see from your log at this point when you're going back and making sure your transaction is correct, if you can see that you had an undo log entry, meaning that I've gone and applied some operation that I have the ability to undo, you know that you need to tell the coordinator about it. If you've only read data, so I've only gone through and I've read data, you can let the coordinator know, but you don't really care about it. Because if you had a read-only transaction and somebody told you to undo it, what are you going to go do? You can't go back and wipe the minds of the person that read the data, so you can just say, if I've read it, you can give a special vote to say, I'm voting on this, but I only was a reader. I didn't really do a lot of work, so we don't need to keep me involved in this. You did nothing, and you received it, you can do the same thing, more or less. But does that answer the question? So the takeaway from that question is that when you vote, if you did a read-only operation or a read-only sub-transaction or a read-only component, you can let the leader know about that, the coordinator know about that, so they can take the appropriate action in order to not keep you in the loop, because you're not necessary. We have a subordinate that fails after potentially received the message or potentially not. But we know for one thing that's certain, it hasn't written out the entry to disk. Right? This force write hasn't happened yet. So what does it need to do?
Same thing as 3.
Same thing, right? Same thing as 3. We're blocked. I'm blocked on it. I need to know what happened so I can make progress. So in which case, you want to check with the coordinator and say, what happened to this? I need to know. The coordinator here's information about it. So if the coordinator at this point in time, it's told everyone to commit, does it need to retain the state of that transaction? So the coordinator at this point, when I tell all of my subordinates, yes, commit, and I forget about it,
Still need to around in case the subordinate crash has to.
yes, just what we just talked about. If it crashes, the subordinate crashes, and it asks you, you need to know about it. So we need to hear about it. If we know that we've written it down and we pick back up when we failed, do in this case? Or let's think for a second. If we're designing this protocol, and you're a coordinator, and you send out a commit message, you have all your friends, let's say it's Friday night, and again, you send out text to all your friends, say, hey, you guys want to, we said we're going to hang out on Friday at 7, and I told you, yes, we're going forth. But one of your friends hasn't said, okay, I hear back from you. What are you going to do? Well, you're what? Yeah, if you're annoying like me, you'll resend it. You'll harass them. Hey, I said we're doing this. Did you hear back? Hey, I said this. What are you going to do? So what's going to happen is if the coordinator hasn't gotten acknowledgement back from all of the subordinates, it's going to periodically send out commit messages back to the subordinates. It's going to say, commit, commit, commit. So if somebody fails and comes back online, I'm going to get that commit message, and they'll acknowledgement, and they'll send it back. We have a failure at the coordinator at this point in time. Okay, it's received acknowledgement, some of the acknowledgements, not all of them necessarily. What's it going to do? Well, in this case, it's going to do what we just talked about. It's going to rebroadcast those commits periodically until it hears back. So what's kind of the message here is that a coordinator is going to rebroadcast commits, so when a subordinate hears about it, it's going to acknowledge it. So if we hear about a commit, we're just going to send back an acknowledgement. But at some point in time, the subordinate needs to forget about this transaction. It can't hold on to this transaction forever. It has to let go and move on. So at the point in time that we've done this, we want to forget about it and just say, if somebody asks me, I'm going to say I committed it. We know by the protocol, at this point in time, that I've safely committed it. I wrote it out to disk. I have this commit in disk. The only way I'm going to acknowledge this stuff is say acknowledgement. I heard what you said. Doesn't really matter if they've done it. So if we write the end now, it's not a force write, but we just write it. We've recovered that. We're only going to be able to say that we hit 9 as if that end actually made it. If the end didn't make it because we didn't force the write, as the question was earlier, the end might not make it. But we know we can reconcile this pretty easily. This isn't a worst case scenario because we just resend out the commits. The subordinates will say, yes, I heard you were doing it. You're annoying. And we'll go on with the business. But the subordinates here have released. They've already let go. They're on processing. So this isn't as a critical section here. So this is part of the reason that we have to force write. So if there's a failure and a recovery here, it doesn't really matter. The transaction's done, everyone's committed about it, and actually everybody's forgotten about it in this case. So hopefully through walking through all of these steps of what can happen in every little point of failure in here, that you're somewhat convinced that this is actually a pretty good thing to do.
Are subordinates only able to process one of these at a time?
On one set of locks that they have. If you had a lock on one set of data, you're prepared on that lock of data, you can't do anything else to that data because you're committed to that data. So if you had a disjoint set of data, you would be able to process more than once. It would be depending on how the implementation sets up.
So maybe this doesn't happen in practice, but if they could be doing multiple of these at once, maybe you could run out of room on your log with commits, and then you wouldn't know that you had committed, or that the whole system had committed at that point?
Part of the force write is that you don't return, the force write doesn't return until it actually writes it out. So if for some reason the storage became unstable or you ran out of room, you would never hit that force write, so you would never be able to, so this would become a blocking function effectively. So it would never return, so therefore it would never make progress past that point. So you could treat it effectively as a failure before that point, and the same thing would happen. So it's like this write couldn't happen for whatever reason, this is just going to keep sending commits until it can make progress. If this force write can't happen for whatever reason, it's going to abort the transaction.
So what is the difference between like 2 and 6? Did you already complete
The difference between
2 and 6? Force write on
this, before 2, the subordinate hasn't committed to do anything. So it hasn't made any commitment about what it's going to do. So once it crosses this boundary, it's prepared and it's locked, and it can't do anything until it hears back from the coordinator. At this point in time, it's kind of in the same gray zone as 3 here. I've already committed to it, and now I'm waiting to hear back from it. The abort can happen at this point in time too. The abort is a little bit different protocol in terms of once you've aborted, you don't care about it anymore. The coordinator actually, if you abort, won't send the message to you, and you're just going to move about your business. You've aborted. It's a unilateral abort. You don't have to worry about somebody, you don't have to worry about being overwritten in this case. If it's abort, we forget about it, we move on. All we can hear about is an abort, or we can get a request from the coordinator to say, what are you doing? In which case we'll tell them, hey, we aborted that. Does that answer that question? Again, read-only sites, we talked about a minute ago. If you didn't apply an update, you can say that I vote, but I only read data. Now, I won't get into too much of the details of this protocol, but there's an optimization in the reading assignment. And one of the observations is that what happens in this protocol, in the lack of information, you abort. If the coordinator hears about something and recovered, it's going to abort. As long as you haven't prepared, abort when it's not the case. So if we can make an optimization on this, which is called two-phase commit with presumed abort. In this case, what we basically don't have to do is we don't have to write aborts out to the log. We don't have to send abort messages, although you still probably want to. It'll be a good thinking exercise to think about how does the protocol change if I were to assume aborts were the same. Conversely, you can also assume, well, I'm going to assume that things go well. We can have a presumed commit if things go well, and we'll figure it out otherwise. Does anyone have any questions on two-phase commit? All right, we're going to move on to distributed locking. We'll take a 5-minute break, but before we do, take a few minutes to think about locking and deadlocks and what can arise in this distributed environment that might not necessarily arise in a localized environment. So 5 minutes, do some jumping jacks, wake up.
Yeah, to go for just that you like this skills. Sense the protocol. I think I sometimes err on the side of giving too much preparatory to
Pretty standard. Well, we're playing pretty standard. Yeah, I just heard of this.
Those tricky, like, tricky places. So,
I don't know how to.
I would probably wait if we want to do a little bit more. 3.5.
Well, that was interesting for me. Like, this is just like, put it on right, like, double, like, it's a pretty small race. It feels like to me he wants me to stay in the box. And he's raising now because he knows he can get value. This is not a raise. I feel like he has a pocket fair like worst case, in some case, I'm going to make $5 to see if I get it. No way I re-raise. I probably call it. At least especially in the city. This is pretty much checkable. Like, I pretty much it's not a force. What did you do? I was, we should get that stuff. What did we have? Yeah, Jack. Sorry, not Jack. Yeah. You don't have that one. I had 2 hands for I read it to Jack. So, next 2 days,
Alright. So you guys, I know all the chatters about the problem. Alright guys. I'm glad you're more awake now. Alright, let's think about this problem now. We want to think about locks, how they're managed in this environment. If we think about this distributed shared nothing world, what's going to happen is that's going to be locks associated with data. And we can associate those locks with the actual data. So the entity that owns a data item is responsible for the lock with that data. This is the case that way if we execute the transaction, we need to acquire a lock on that site. That site's the one that has to give the lock. You could think of some alternative design where all the locks sit in one site, and anyone that wants to lock a piece of data has to talk to that one site or that one partition, that one node, and say, you know, I want to lock item A, I want to lock item B, and this site's responsible for handing out locks and doing that. If you think about it, that doesn't sound like a great design, right? We know that there's a lot of locks or latches being acquired and released throughout these transactions. And having one site be responsible for all of them does sound like a bad idea. One case, well, if that gets, you know, slammed with work, it's going to become slow in acquiring locks. If that site goes down, we guess what, nothing can make progress. So in the shared knocking world, we want to think about what's going to happen if we associate a lock with the partition that actually has the data. The question is to think about deadlocks. When we talked about 2PL, we talked about cases that can arise for deadlocks. Does everyone remember what a deadlock is? Have some transaction. It's locked on a lock held by some other transaction. That transaction's waiting on a lock from transaction 1. This is a case where you can't make progress. You have two transactions that are sitting there. They're blocked. They're busily waiting for the lock from the other transaction. We can't make progress. We talked about a centralized site, a single site. We resolve this through deadlock detection. And a nice way of doing deadlock detection is looking for cycles in a graph. We can do that. If we think about the world over here, though, let's say where we have two sites, and there's transactions running. Transaction 1 here has acquired a lock on A. Transaction 2, which arrived at the site, is now waiting on that lock for item A. Site B has item B, and it's a different order of the transactions. Here, transaction 2 has already acquired the lock for B, and transaction 1 is waiting for B. Now, if we looked at just this site in isolation, that doesn't look like a deadlock, does it? We have transaction 1, we have transaction 2. Transaction 2 is waiting on transaction 1. This is what's happening at this site. On this site, though, we have transaction 2, and transaction 1 is waiting on it. So in the global scheme, if we step back and look at this, do we have a deadlock? Put these together. T1. This is a deadlock. We have two transactions that are blocked on each other, and they're not going to make progress. We have a global deadlock. This is what we're going to come up to be a distributed deadlock. If you looked at the sites in isolation, it doesn't look like there's a deadlock. But in the global scheme of things, these transactions aren't going to be able to complete because of that deadlock. Does everyone see why this is a problem? Are they different what?
Different pages.
Yeah, they're different pages.
So,
And A is located on this site, and B is located on this site.
if you want to just work on one page, you work on that.
Well, that could be the case, but let's say the transaction was read A, write B, and we had exclusive locks. So we write A, write B, and that was our transaction. With two-phase locking, you acquire your locks as you go. So here, the case is to grab the lock in A, and it says, I want the lock on B. That's all it's sitting now. It's saying, oh, somebody has it, I'll give it to you in a second. And the vice versa case happens. But I need both of those locks in order to process my transaction. If the transactions were independently A and independently B, there's no problem. Does that get it? Okay. That is a good question. So what's the solution? What can we do? Hmm? Sorry? Sorry? Yeah. So we can have some kind of coordinating process. So what we want here is we want to wait for. I want to see what transactions are waiting for what. And if we have some kind of coordinating process, some kind of thing that's responsible. It can pull all of the sites and say, what are you waiting for? So we could get this information. And when this gets the information, it can collect it all back up, it can put the pieces together and says, you know what, we're not going to make progress. We have a distributed deadlock. So this could be expensive, it can be complex. We have to figure out how can we do that. We can think about optimization, that we could maybe have sites only communicate when they're waiting on somebody. So T2 could let this site can let this site know what it's waiting for and vice versa. You could get cases though where you have transactions. We have a cycle, and these sites might be distributed. So doing a localized communication, if you build something along this nature, you're going to have to make it transit. If T2 is waiting on T3 and T3 is waiting on T1, well, when T3 lets T2 know, it needs to say, hey, you know what, I'm also waiting on T1. And T2 could say, well, you know what, I'm waiting on T1 also. But T1's waiting on me, we have a case here. So we need to think about how can we actually do this. But this actually becomes...
Isn't this just like going back to what we didn't want to do, where we said one central locking place?
So that's a good question. So we don't want necessarily one person responsible, so we could localize it in this case, where you actually just communicate with each other. So in this case, when we had this transaction, if these sites only exchange information with each other, not some global coordinator, then they could resolve between themselves. We're stuck. In this case, we can avoid that. What we need to do in this case, if we avoid it, then we have to have some process, some way of deciding which transaction to add. In the coordinator case, the centralized case, we can do it. In this case, if you want to be distributed by it, we need more of a democratic approach. So here in this case, you can come up with some complex way to say, well, what was the more complicated transaction? What spent more time? What's going to take longer to redo? But that becomes expensive. So maybe just flip a coin into it. But this is a good question. The question is, we want to avoid these kind of things. So the simplest solution, and what a lot of people end up doing, is timeout. We build a distributed database, we just go forth and we say, I'm going to wait only a certain amount of time when I have some locks being held, and if they're not acquired in some time, I am going to abort that transaction and go about its business, and that's it. And that's just basically a timeout mechanism. We talked about those main memory databases in HStore. That's built on timeout mechanisms. It's not the ideal case, because there's cases where it's asynchronous communication. You send a message, you don't know how long it's going to take to get back. You don't know if that machine is busy. You don't know if the network is necessarily congested. So you might actually abort transactions in that case that you didn't necessarily want to abort. You might also just have a really slow transaction. It's processing very slow, or it's requiring user input. In this case, it does horrible. But this is a decision that a lot of systems are doing. We want to keep things simple in order to do it. A related issue.
Does that lead to live lock?
For like starvation?
Couldn't you end up in the same deadlock again, board it again, or timeout?
Yes. If you had some kind of, I guess, deterministic approach where basically every time we acquired the same locks, we got to the same point over and over again, I don't know what the real solution is, you know?
I mean, the standard solution to these live lock things is to use some kind of randomization so that, you know, you either tweak the timeout by a small amount of time each time, or wait some amount of time after you kill one of the transactions. Some small random amount of time, just so that you don't get these kind of synchronized patterns where things do the same thing over and over.
Yeah, I guess the odds of it happening would be low, but that would be a simple way of doing that. Thanks, Sam. Another issue that kind of comes up that's related but a little bit different to distributed deadlocks is coordination. I just talked about this asynchronous messaging taking a while. We don't know necessarily how long it's going to do. How long is a message going to take? It makes synchronization of operations very difficult. There's a simple example of the two generals. In this case, if we had two sites, site A and site B, or in Sam's notes, Barack and Hillary, but basically, site A says do something like attack it down. It sends the message over. We get the OK, sends the message back, and then at that point in time, it wants to say, let's go, and we get back the confirmation. Well, in an asynchronous world, this becomes very difficult. For everyone that took distributed systems, this probably seems pretty straightforward. But when we want to coordinate processes, and I don't know how long the message is going to take, and we rely on these multiple trips to actually establish anything to go forward, getting any kind of lockstep operation between your databases becomes extremely difficult. There's also a probability that any one of these messages can fail. So anytime we design a new purpose, we need to think about these issues. But we have to operate in this kind of like messy, slow, asynchronous world. Any questions on distributed deadlocks? Well, let's move on to replication. Everything we've talked about so far is saying we want to partition data. I want to take a database and I want to slice it up. I'm going to take my table of customers, and based on what state they live into, I'm going to give them into different sites. This isn't the only world we want to operate in. There's a lot of times we want to actually replicate our data. I want to make a copy. Every customer appears on more than one machine. Now, obviously we want to do this for fault tolerance reasons. Maybe the one machine dies and never comes back. I don't want to lose that data forever, so I want to replicate it. It also might be for what we want for load balancing. When we're issuing these queries out to these partition sites, when we did distribute these queries, before we only had one option. If I wanted to send, a read about all my customers in Utah, I only had one place to do that. If that machine was slammed, maybe it's California hashed to the same machine, I have no options. If I took that data and replicated it, made 2 copies of it on 2 different machines, I now have options for load balancing. You could also use replication to maybe move a copy of the data closer to a customer. We've talked about these things like two-phase commit and these operations in parallel databases. And assume there's like this cluster of machines and they're tightly coupled. A lot of these database systems that we're going to build are actually going to be distributed. They might operate in different data centers. If you guys go use, Amazon's cloud computing, you can easily fire up a computer in Oregon, a computer in Virginia with a few clicks, and we can set up a distributed database that runs in these 2 data centers, all the way across the United States. Sending one message from Virginia to, let's say, Oregon or California takes on the order of about 80 milliseconds just for that message to get there. So for applications, we want them to be as fast as possible. Say, well, if you have 100 milliseconds, Amazon has said that your shopping cart rates go down as soon as you have 100 millisecond delay in basically processing things. So we want to maybe copy the data so it actually can be physically closer to the customer. So we have to think about this. Replication isn't free, though. If I want to copy this data, I have to think about, well, what's the state of this data? What's my protocol that I'm going to use to replicate this data between these machines? How can I reason about that protocol? Now, replication is a loaded term. We have replication in distributed computing, we have replication in databases. Sam and I were even talking earlier about just the myriad of terms that people use within the database community. So I'm going to say some terms. If you go forth and you see other terms, don't assume that I don't know what I'm talking about. There's just lots of nomenclature in this term. So we think about replication. Let's think about one mechanism that we call synchronous replication. The synchronous replication effectively means when you issue an operation within this update to one site, and this site has a replica, the site won't respond to you until it's applied that update to the replica. This is also sometimes called eager replication. If we've gone through these protocols, think about that. What's the benefit of waiting until the replica has applied the update before we tell the customer?
No, you can use any replica immediately.
Well, that's a good point. Now we have 2 replicas that are the same. So somebody could issue a read to the other replica, and they should see the same state, especially if we use a protocol like two-phase commit to make sure we're in a lockstep. The other issue is, what if there's a failure at some point? If the replica doesn't get back to the client doesn't have to think about if it made it or not. Let's think about the other protocol that we can use. Asynchronous replication, or lazy replication. So in this case, what's going to happen is when a site, a database, receives an update, it will send that update to its replica at some point in time. But as soon as that database has applied the update locally, it acknowledges it to the client. It tells the client, I've received this update, I've applied this update, it's good to go. So in this case now, as the question just pointed out, that that means that we could have two sites with two different views of the data. If I update the data in one site and say, you know what, the customer's, Bob's salary is 120, the other one says it's $100 an hour. Well, now you have two different views of that same data. We'll get into this a little bit next time. But the other issue here is, what if the site that you applied the update to fails before it sends the update to the replica? In this case, you can have another data set sitting out there somewhere that has a different view of it. So these are two pretty drastically different ends of the spectrum in terms of how are we going to apply updates and how do we interact with the clients. There's also a pretty popular way inside industry we'll get into a little bit, which is called semi-synchronous. And this is a little bit of a hybrid approach where basically before a site responds to the client, it ensures that the replica has at least acknowledged that this update is going to happen. It doesn't necessarily mean that it's applied, so it's not in a consistent state, but we know that the ability to do it is somewhere else. So it doesn't really offer us any guarantees about what's going to happen, but it's used in a lot of cases as immediate. Now we can see that there's pretty drastic performance differences just in these two protocols, right? Synchronous is going to be expensive. It means every update that I apply now has to be set to multiple copies or one copy before it responds to the client. So this can involve a network trip, the application of that data somewhere else, and it has to be sent back. But even inside of that, if we have multiple copies, we have to think about what's going to happen. Let's say there's 10 copies of the data, and I'm replicating it 10 times. How do I ensure that it's consistent? Well, one thing that we can do is we can do what's called read in, write all. And here what this means is when the synchronous replication happens, it has to write the data to all of its copies before it acknowledges. But if I do that, then you can read from any one of the sites. You can just go forth and issue a read to any one of my replicas, and they're guaranteed to tell you the same thing. The other approach that we can do is a vote approach or a quorum approach. And here what you're doing is you're going to specify some number of readers and writers that you're going to issue in order to give a consistent operation. So let's say I had 10 replicas, and my write set was 7. That means as soon as 7 of my 10 replicas acknowledge that they had applied it, I'm good to go. But then in order to have a consistent read, you have to read from at least 4. Right? This is our 10. We applied it to 7 of them. My read, if it's 4, I'm guaranteed to at least talk to one of the nodes that was involved in the write. This way we can at least detect the conflict and figure out, maybe based on timestamps or some kind of other logical counter, which is the most current operation applied. So within synchronous replication, we have these two standard ways that we can apply it. Within asynchronous replication, there's a lot of different ways that we can do this. One is that we can actually ship our log. We've been talking about the write-ahead log always as this kind of authoritative state of the database. But when we apply updates to this log, we can have a process that listens to the log and ships these log entries out to the secondary, the replica. And that secondary replica can apply those updates locally, like it's replaying the transaction, which it can just stay up to date by listening to the transaction log of what we call is the primary. Another approach is we can use snapshot. That we can take an actual picture of the database and ship it over, and then somehow derive deltas of that and ship that over at a later point in time. Now that's obviously expensive, but it's going to actually improve the performance of it. A lot of times people end up using that log shipping as a way of doing this kind of replication. Now, there's another concept that we have to think about when we think about replication, which is how can updates be applied? The standard approach that we'll see in a lot of these cases is going to be something called primary copy. What this means is that updates have to go to one site. There's a primary, it's responsible. You'll occasionally see this in older literature referred to as master-slave, but in modern literature they're going to say primary, secondary replication. And so this is just going to say that updates go to one node and it's responsible. It effectively acts as that coordinator process that we talked about in 2 days today. The other approach, and again this has a lot of terms for it, it's most typically referred to as multi-master. Now so multi-primary. Right? Now it's the peer-to-peer. And in this environment, updates can be applied to any site. There's not one site responsible, but I can send these updates to any site. Now, if you notice, these techniques of how updates can be applied are what's responsible or orthogonal to this issue. It makes sense to have one case and another case. Multi-master makes more sense than synchronous, so I can keep everything in line. But there's not a reason that I can't apply multi-master with asynchronous. On Monday, we'll get into some of the issues that might be about it, but hopefully you can see at this point in time that if I had this asynchronous replication, updates are being applied at a lazily rate. Updates can be applied anywhere that you can get yourself into some trouble. The same concept, primary copy, can be used in either case. Now, for the most part, when we talk about two-phase commit, these kind of consensus protocols, you'll see them being used more in local area networks. They're expensive, they're dependent on a master being up or a primary being up in order to be the coordinator for this process. And when I talked earlier about this motivating example, you could have a wide area network, a database that's replicated over a geographic area. In which case, this primary copy, this two-phase commit, might not be the best approach. Taking the distributed systems class, Paxos forum, Leslie Lamport, who wrote Paxos, is speaking in 10 minutes, I believe. I think it's data, but it's a protocol that's used for actually kind of dynamically electing the coordinator. It's an interesting protocol. We're not really going to get into it because it can take quite a while to understand the details of it. We're just